things that were sequences, right? Like different kind of number patterns. And today we're going to take those sequences and we're going to do summations. So we're going to start adding them up. One of the types of story problems that your book has a lot of is like seats in a movie theater or seats in an auditorium. So think about RPAC for a minute. There are a certain number of seats in the first row, right? And then just because of how it is, and maybe actually Wharton would be a better example. Wharton has a certain number of seats in the front row. There are usually like what, 2 more in the second row? And then 2 more in the next row. Do you see how that would give you a sequence? Yeah. So if you wanted to know how many seats there were, you would do what we call a summation and you would sum up the values of all the rows. Well, it turns out there's a formula for that. There's a formula for most things, right? So when we're looking at sequences, we have these things called partial sums. And partial sums are where you want to do a summation up to a certain point. So maybe you want to know how many seats are in the first 10 rows. Like maybe those are your VIP seats and you're going to sell them, and how many of them are there? Well, you'd have to add up the value in each of those 10 rows to get the partial summation. So the notation is important here. S sub 1, right? Little subscript. S sub 1 is just A1. S sub 2 would be the sum of A1 and A2. S sub 10 would be 1, 2, 3, 4, right? The subscripts all the way up to 10 added together. Does that make sense? So this is basically telling you where to stop. It's saying add up until you get to A2, A3, A4. So these are called partial sums, and there are a couple ways to think about them. One of them is with sigma notation, which is fun, I think, and I'll show you that in a minute. The first way we're just going to kind of talk about in general. Okay. Okay, so let's do a couple example problems. This is kind of one of those moments where we jump in. We want to find 4 partial sums, and then we want to find an equation that could give us the nth sum or any sum that we ever wanted to find. So that's where we are. So let's start by finding some of the terms. So go back to Friday. Remember, we were just finding terms. If I want to find A1, what do I do with the 1? Plug it in. 2 times 1 is?
2.
Minus 1 is?
1.
Okay. A sub 2, we plug in the 2 and we get out what?
3.
3. A sub 3. Let's keep finding them until we get up to A sub 4. So let's find 2 more. What's A sub 3? 5, and then 7. Okay. All right, so let's start finding the summations next. So the first couple summations aren't so bad. It's the one where we need to kind of make it an equation that's going to be a little tricky. So S1 means just what is A1? It's 1. Not exciting. S2 wants me to take the first 2 terms and add them together. So I get what?
4.
S3 wants me to take the first 3 terms and add them together. I get
9.
S4, first 4 terms. 16. Okay. Now, we want to make a formula that can help us get any summations down the road. So we don't have to, because if I wanted the partial sum of 17, do you really want to find the first 17 terms and add them up? No, that doesn't sound like a good time. So we want a way, we want an equation, so we could get any partial sum when we want it. Let's look at the relationship. The partial sum for 1 is 1. The partial sum of 2 is 4. 3 is 9. 4 is 16. What's the relationship? Squares. So is it fair to say that your partial sum, we're going to call it S sub n, so we could work with any subscript. Is it fair to say that it would be your n value squared? So if I wanted to find S sub 10, I wouldn't need to go all the way up and then add all of them together. What would S sub 10 be for the partial sum? 100. So what we call that, so I don't know if I told you guys the story, but back before I decided to be a math teacher, I finished at Michigan State, and I finished in the winter because I played sports at MSU, and so I couldn't take full loads of classes. I mean, I took full loads of classes, but I took 12 credits exactly. So I graduated in the winter, and I started getting weird emails. And it wasn't as weird back in the day because scamming wasn't quite as big of a thing, but I started getting emails from the U.S. government, and I was like, that's weird. And they wanted me to come and work for them and be a cryptologist. So a cryptologist is somebody who breaks and analyzes code. So for a while, I thought maybe that's what I was gonna do. But then I started like getting into schools and actually teaching, and I loved it. And I was like, no, this is what I want. Also, the cryptology stuff sounded stressful. Yes.
Did you play, do you want tennis at?
Yeah. No. So, anyways, with the cryptology stuff, my point of that story was we have this word when you go into cryptology called brute force. And brute force is kind of what it sounds like. It means you are going to do a lot of work to get the answer. So this way, listening, this way is the nice equation way. The brute force method for S10 would be to find the first 10 terms and then actually add them up. Like, could you, I'm going to use brute force a lot. So could you brute force it and find the answer? Yes. Are we going to? No, because I have a nice equation for that. Does that make sense? So I will say brute force sometimes, and that's what I mean by that, is that you're going to go through and you're going to actually find all the things one step at a time. It's time consuming, but doable. Okay, same thing, different problem. Here we go. Sorry, story time's over. A1. We're going to plug in 1. So 1 over 1, and actually, I'm going to leave this kind of funny looking. Okay, I need you to stop talking. I'm going to leave it as these two fractions, and you'll see why in a second, because I'm going to be able to see the patterns better. So when I plug in 1, 1 over 1. When I plug in 1, 1 over 2. 1 plus 1, 2. Good? Do the next one. Again, you're going to see the patterns a little bit better this way. Oops, I almost made it a 3. We don't want to jump to 3. This is going to be what? 1 over 2 minus 1 over 3. Okay, so find A3 and A4. I think you can without even plugging them in, right? Follow your pattern. So this is a situation where I would actually prefer you not to simplify, right? Normally I would say simplify that. You know it's 1. This is the spot where actually that doesn't help us. All right, let's start finding our partial sums. S1 is going to be 1 minus 1/2. And actually, I'm just going to leave it like that. S2. So let's actually write this one out. I'm not going to make you write all of them out because you're going to see the pattern in a minute. Okay. When I write that one out, what happens to my 1/2? They cancel. So this is really 1 over 1 minus 3. Do you think you might know the pattern? S3. I'm going to add them all together. So I get a negative and a positive, a negative and a positive. So the middle stuff is canceling out. What's going to be left for S3? The 1 and what else? Minus 1/4. And actually, I'm going to rewrite this as just a 1 to make it look identical. All right? So S sub 4 would be what? Without doing anything, what is it?
1 minus 1.
1 minus 1/5. Okay, now, if I asked you to find S sub 20, could you, by brute forcing it, right? You could. Do you want to? No. Could you? Yes. All right, let's make a formula for this. What's my formula every single time? What's the first number always?
1.
minus, what's in the numerator? Always. 1. How does this number relate to this number? Always. Yeah, it's our n, but 1 bigger than that. So this would be my formula here. This would be my formula here. Again, can you brute force it? Yes. Do you want to? Probably no. So that's why we make these formulas, so that way we can get our answers without spending the entire day on a problem. That's not fun. Okay, we're summing things up, agree? Summing things up means we are using a notation without knowing it called a sigma notation. I'm going to have you add this into your notes first, and we'll talk about what it means. Because sometimes it's not always easy to write it down and process all the things coming out of my mouth. Let's go. Write it down. I wasn't going to. I didn't plan on it. So my roommate, I lived in Holden. And you know how the tennis courts are right in front of Holden?
Where's Holden Hall?
Holden Hall on Michigan State's campus. And so my suite mates were both tennis players. And so they're on the tennis team. And they were like, let's go play. Like, I was like, oh, yeah, play in high school, let's go play. So we went out to play. And they were like, you should probably try out. And I was like, and then I did. I was a walk-on. I was very much a walk-on.
Did you play like on?
Because when I got up to organic chem, math above Calc 4, it wasn't working.
You couldn't like do other things.
I couldn't get the grades I wanted to get. And I was like, yeah, I'm not going to be a professional tennis player. Like, I'm not even starting. So, like, I'm going to go ahead and pay my cash.
It's so cool that you did that. To get scouted. We're going to yell your name.
Yeah.
Which was so?
Yeah. Nice. I think Ann Taylor lost from like 20 years ago, though. So, like, I'm not a new play buyer.
It's nice though.
Thank you. And what's funny is it probably went out of style and has already now then come around back in where it's cute again. Is probably what has happened. All right, do we have everything written down? All right, now I need you to listen. So we're not talking, we're listening. All right, so let's say you have a sequence. A1, A2, A3, so on, all the way up to A sub n. We want to use summation notation, which is the same as sigma notation, to talk about adding things together. Often, the letter that we use for a variable in summation notation is K, but sometimes your book likes to use I. Now, I don't love when they use I. Why is I problematic?
Because it could be other.
Yeah, it could be imaginary numbers. So I don't love it when they do that, but sometimes they do, so be prepared. And just in life, not even just in your book, sometimes in other math classes too. Okay. I still need you listening to me. So K is going to be, or I, is going to be our variable, or the index of summation. It's the summation of variable. And then we are going to replace K with our natural numbers, with our values that we put in to count. Now, depending on the equation, we could even get into integers, meaning you could even start at 0. And we'll talk about how you can alter the equation so you can add the integers in as opposed to just the natural numbers. And the summation notation means please add it all together. Okay, so this is kind of small. Let me draw it a little bit bigger. So this is your summation notation. We live close enough to Michigan State to know that that's a sigma, right? All right, now, down here, it's going to tell you where to start. Sometimes it'll say K equals 1, sometimes it'll say I equals 1. Again, it just depends. This is your starting spot. So this part tells you where to start. And then there'll be a number here. There won't be an end. There'll be like 5 or 17. And this number tells you where to stop summing. And then you will have something here. And you can calculate all the terms. So let's say it went from 1 to 5. You would calculate term 1, 2, 3, 4, 5 and add them up. So we're still doing the partial sums we were doing a minute ago, but now we have this new sigma notation. And I want to make sure you're paying attention to it because in calculus, before you start learning, you know how there's always like a harder way and then a little bit easier way? We show you the easier way after the harder way, right? Okay. When you start learning about integrals in Calc 2, and I think a little in Calc 1, I'm not sure, maybe, you use this notation a lot. They're called Riemann sums, and you're summing up the area under a curve. So,
Ms. Vessel,
yeah.
can I get Ajay to come stay at this?
She is not here.
Okay, thank you.
Okay, so let's look at some examples and start going with these so we can see how it's used. All right, do you see how this one tells me? Start at 5. This is my formula. So if I start at 5, k equals 5, I like to write it above. You don't have to. If I plug in 5, what do I get? 25. So term 5 is 25. Plus, let's go to term 6 because we need to go from 5 to 9. And remember, we only do whole numbers. So if I plug in 6, what's that value going to be? 36. If I plug in 7, 49. If I plug in 8, 64. If I plug in 9, 81. Do I need to go further? No, because this is my starter, this is my stopper. Now, these we are going to brute force. This isn't as much of brute force as it could be, but we're going to add them all together. What do you get? Oh, now I'm wondering if that was a cubed. We're going to pretend it's squared. Miss Vessel apparently can't see.
Yeah, that's what I was.
It may have been a cubed. We pretended this was a square, though. Now that I'm looking closer, it may be a cube. You guys, I even took an eye test the other day, and they told me again I was 20/20, and I'm like, I don't really think that's right. Okay, add them up. What do you get? 255. Me too. So that would be your answer. So these are still partial sums. It's a different way to write it with a sigma notation. And again, why is it good we see sigma notation now? Because it's going to come back in calculus. So we need it. Oh, they switched to I already. Look. All right. What term do I start with? 2. So if I plug in 2, do you see how it's just I? So it's just 2. That's not very exciting. So that's I sub 2. I like to write them above because it makes me feel better that I've accounted for everybody. You don't have to. What's I sub 3? 3. And then 4. Where do I stop? 9. Okay, add them up. What do you get? 344? Oh, just 44. Yes. I was going to say that's way too big. 44 I agree with. Okay, the next one's kind of funny. I'm going to start at I sub 2, and I'm going to go to plug it in. Is there a spot for me to plug in? No. So guess what? It's just 2. What's I sub 3? 2. What's I sub 4? What's I sub 4? 2. Yes, I sub 5. Do we see where we're headed with this one? And again, part of the reason I like to write them out up top is to make sure I have enough 2s. Because I I need to start at 2 and go all the way up to 7. So again, Miss Bethel likes to write those out because it makes me feel better and I know I've accounted for everything. All right, so if I have 6 2s, what do I really have? 12. All right, now we're going to work the other direction and we're going to be given the sequence and we're going to write our own sigma notation. So this is where I'm going to show you that you could have like a situation where they wouldn't be just counting numbers. All right, let's draw our sigma. Draw your sigma, friend. All right, what am I doing to each thing? Raising it to the 4th. I'm going to use k because that makes me feel better than I. So I'm taking each thing and I'm raising it to the 4th power. Where do I start? 3. Where do I stop? 9. Good? Okay. Now, the part B says, though, we want to write it in a different way. So let's come down here. Give me a sigma again. Let's say it says we want the same answer, but we want a different equation, a different sigma notation. So take a minute. If I put in k plus 1 instead of just k, I can do that, but it's going to change these numbers. Does that make sense? So if I put in k plus 1, I can do that, but then where would my first k be? 2. And what am I going to go up to? 8. So do you see how if I went high enough in what I was adding, I could get into some negative numbers? Okay. So that's why we say integers instead of just natural numbers here, because we could get ourselves into a situation where we could backtrack enough that we would have to start in the negatives. Are you ready for homework?
Yes.
Yes. Okay. This is another notation that I feel like is really good to see in this class, and not for the first time when you get to college. I do get excited about stuff like that when you see something now that you'll use later. Assignment 2, page 793, numbers 33 to 36, 41 to 43. That's not a lot. Yes. Why would I stop at 8? Because when I plug in 8, 8 plus 1 is 9, so that would be this one. And if you look at it, do you see how it'd still be the same number of terms? So that's another way to think about it, is making sure the number of terms you're adding stays the same.
Yes, I see the one.